let's continue talking about topic 2.1, kinematics, and today we'll talk about free fall and a specific type of acceleration, the acceleration due to gravity. We know that if we drop something, it falls. This falling action is caused by something that we call gravity. It's a force that we're going to talk about more in depth when we get to dynamics, but for now it's enough to know that it acts on all things. It pulls all things down towards Earth, and it causes all things to accelerate at a uniform rate. And remember the difference between acceleration and velocity that we talked about last time. Acceleration is the rate of change in velocity. Velocity is the rate of change in position. And so when we say that gravity causes all things to accelerate at a constant rate, they're not all falling with the same speed. They're all speeding up at the same rate. And of course that acceleration is always acting towards the Earth. And because the acceleration is always in the same direction, it gives us some symmetrical paths that we can analyze when objects are being thrown up or falling down. The magnitude of that particular acceleration that has been experimentally found on Earth is around 9.81 meters per second squared. And that does vary a little bit depending on your altitude, and we'll talk about more about why that is a little bit later on. But if we look over here on the right, and we'll just kind of use this little diagram to talk about a couple things. Here we have a person throwing a ball straight up in the air, and for this particular scenario we're going to round this, and we'll do this a lot just for ease of calculations. We're going to round it up to 10 meters per second squared. And if we're using this and if we're rounding, I'll let you know. Don't do that unless it's specifically stated, but here we're going to just for this example. So our little guy down here throws a ball up with an initial velocity of 30 meters per second. So the instant it leaves his hand, it's traveling 30 meters per second in the upward direction. That's our velocity vector. As soon as it leaves his hand, it's accelerating though. As soon as it leaves his hand, it's starting to slow down because of the acceleration due to gravity. And so it's slowing down, slowing down, slowing down. It travels some distance in that first second, but at the end of that first second, it's moving 10 meters per second slower because it's slowing down at a rate of 10 meters per second every second. And so after 1 second, it's traveling 20 meters per second. After 2 seconds, it's traveling 10 meters per second. And after 3 seconds, the velocity has dropped to 0. And this is our peak. Okay, the peak is this point at the very top of the path where the velocity for an instant is 0. But that acceleration doesn't stop just because it gets to the peak. It doesn't mean that gravity has stopped acting. It doesn't mean that anything has changed about the acceleration. And so what's going to happen is it's going to continue accelerating in the same direction, but now it's going to be speeding up because the object's going to be falling back down. And so after 1 second from the peak, which is 4 seconds in total, the object is going to be traveling negative 10 meters per second. Because acceleration is a vector, that negative sign tells us it's moving in the opposite direction. So 2 seconds from the peak, or 5 seconds later total, it's traveling negative 20 meters per second. And 6 seconds after the ball was thrown up, or 3 seconds after the peak, it's traveling with the same speed as when it was released, but in the opposite direction. So the magnitude of velocity is the same, but the direction has switched. And if we look at a couple of these graphs, and the next section we're actually going to talk more about graphs of motion, but if we just kind of really quickly look at a displacement time graph, which is this top graph, and an acceleration time graph, which is the bottom graph, we can analyze a little bit more about this motion. And if we think about our axes, this is probably really more accurately referred to as a change in y graph instead of a change in x graph, because we're going up and down in the y direction. But at time 0, the object is here. After 1 second, it's here. After 2 seconds, it's at its peak. It comes back down, and you can see that both sides of this position graph are the same. Okay, so we have that symmetry again. It's a parabola. Our velocity graph, though, if our velocity starts somewhere up here, it looks like it's right about 6. So it's traveling up with a speed of 6 meters per second. It's slowing down until it gets to 0. And notice that 0 corresponds to the peak of our position graph. The acceleration is not changing, and so the slope of our velocity graph isn't changing. And so we see that continue right on down until it gets down here where it's at -6 meters per second for our velocity at the end of the trip. Okay, let's try a couple practice problems involving our uniform acceleration equations and this idea of acceleration due to gravity. So we have a scenario where we have a human cannonball, this guy down here, Astronov, and he's being shot straight up with an initial velocity of 125 meters per second. And again, we're going to use an acceleration due to gravity of 10 just to make our calculations a little bit cleaner while we're working through this. So, of course, the first thing that we need to do is figure out what do we know. We know our initial velocity. U is 125 meters per second. And we know our acceleration. Our acceleration here is g, which is our 9.8 meters per second squared. And here, the first question, we're being asked to find how high does he go. Okay, so we're trying to find height, which is basically our displacement, our maximum displacement from the point of being shot. And so at that point we know another variable that's not explicitly stated but is implied, and that's the final velocity. At the peak, the final velocity is going to be 0, and so here we're looking for the displacement. So if we think about our kinematics equations, we have initial and final velocities, we have the acceleration, we're looking for the displacement, so we can use our equation v squared equals u squared plus 2as, and we're solving for s. So we do a little manipulation of the equation. We're going to subtract u squared from both sides. We'll divide by 2a. So we're going to get s equal to v squared minus u squared over 2a. And here a is g. Our v squared is 0. So we're going to get a negative u squared over 2 times g, which is going to, now we have an equation for displacement in terms of the variables that we know, u squared and 2g. So we're going to plug this in, and we get negative 125 squared over 2 times negative 10. And notice the negative signs here. And what that's going to do for us is they'll cancel out. That'll give us a displacement that's positive, which tells us it's in the opposite direction of the acceleration. And so 125 squared divided by essentially 20 here is going to give us 781 roughly. 781 meters as our answer. Okay, so that's how high he's going to go. Now, how fast is he going after 7.5 seconds? So here we're looking for the final velocity for v, but we still know the initial velocity, that's the same. We know the acceleration, that's still going to be the same. In this case, we're going to use negative 10 meters per second squared. And we're looking, or we also actually have the time in this case. So t is equal to 7.5 seconds. And we're looking for v. So here we're going to say v equals u plus at. Right? And that's going to equal 125 meters per second plus, again, we'll use 10 meters per second squared, and our time here is 7.5 seconds. And I forgot to put units up here in this one, but it's a good idea to keep carrying your units through. It'll help you kind of check your work. Here we see that this seconds cancels out with one of the meters per second squared seconds, and so our units for the initial velocity are meters per second. Our units for acceleration times time also ends up being meters per second. And so we're following all math rules. Our variables have to obey those same things, and so if this was meters per second and this over here was something else, we wouldn't be able to add them, just like you can't add 10x plus 10y and get 20xy. It doesn't work that way. And so what we end up with is 125 meters per second minus 75 meters per second. And so after 7.5 seconds, our human cannonball is traveling positive 50 meters per second. And again, that positive is important because it tells us the direction. He's still traveling upwards at this point. Now, the second part here, it's asking about the speed after 17.5 seconds, so 10 seconds later after this. And so if we simply change the time there from 7.5 to 17.5 seconds, we have that makes one change. So now it's 125 meters per second minus, okay, 17.5 times 10, that's minus 175 meters per second. And now our final velocity is negative 50 meters per second, telling us then that after 17.5 seconds he has reached the peak, passed the peak, and is now falling down with a speed of 50 meters per second. Okay, just a couple last things about acceleration due to gravity. That g value is the same for all falling bodies. The thing that that gets confusing with this is when we start to think about something like a feather and a bowling ball falling, and when you observe that, you observe the bowling ball landing first, the feather landing second, and if they don't land at the same time, if they're dropped from the same height, obviously they can't have the same acceleration. And in fact, that is true because we have what's called air resistance. And air resistance is responsible for this phenomena, for dropping a crumpled up ball of paper and a flat sheet of paper and seeing them fall at different rates. It's another force. Because the air around us is filled with, well, air, molecules, oxygen, nitrogen, all these things that we breathe, those molecules interact with the falling bodies and offer resistance to their falling. And again, we're going to talk more about this when we get to dynamics and address it in forces, but essentially it decreases the acceleration. And that's dependent upon a couple things. The two primary ones are surface area, so larger surfaces encounter more air molecules in a given period of time and so have a larger air resistance. And speed, objects that are falling faster have a larger air resistance as well, because as they fall faster, they hit more air molecules in a given amount of time, more force, more resistance. And as I mentioned, we'll talk about that more when we get to forces, but you should be aware that that exists, and we'll look at some demonstrations of that in class.